Welcome to the deep dive. Today, we're going to be tackling something that might sound a little dry at first,
Okay.
numerical computation,
Right.
but trust me, it's way more interesting than it sounds.
Okay.
We're going to be using excerpts from Chapter 4 of a machine learning textbook as our guide.
Sounds good.
And our mission today is to understand how we get computers, which think in ones and zeros, to handle the infinite world of continuous math.
Yeah, it's a fundamental challenge in computer science, really.
Yeah.
Computers use a fixed number of bits to represent numbers, meaning they can only handle a finite set. But the real number system,
Right.
that's infinite.
Yeah, it's like trying to fit all the stars in the galaxy into a shoebox, isn't it?
Yeah.
So what are the practical problems this creates when we're trying to get computers to do complex math?
Well, one major issue is something called overflow.
Overflow.
Imagine you're running a calculation and the result is so big, it exceeds the limits of what your computer can store.
Oh, like that scene in Office Space where they try to skim fractions of a penny and accidentally create this huge number.
Exactly.
Talk about computational chaos.
And then there's the opposite problem.
Okay.
Underflow.
Underflow.
That's when a number is so small it gets rounded down to zero,
Okay.
which can also cause all sorts of havoc, especially in divisions.
So you're telling me even simple arithmetic can go haywire on a computer?
It can.
That's a bit unsettling.
Yeah.
What type of safeguards are in place to prevent this from causing major problems?
One great example is the softmax function.
Okay.
It's super common in machine learning, especially for predicting probabilities across multiple categories.
Right, like if you're trying to predict whether an image is a cat, dog, or bird, each one gets a probability score.
Exactly.
But how do overflow and underflow mess that up?
So the softmax function uses exponentiation, which can quickly lead to huge numbers, especially with large input values.
Okay.
That's where overflow can hit.
Right.
And conversely, tiny input values can lead to underflow when calculating those probabilities.
So the softmax function needs a bit of a safety net to work reliably.
It does.
How do we fix that?
The trick is surprisingly simple.
Okay.
We subtract the maximum input value from all the input values before doing the exponentiation.
Okay.
This shifts all the values down, making sure the largest one becomes 1 after exponentiation. It's like leveling the playing field without changing the relative differences between values.
That's a neat trick. It reminds me of how we normalize data in statistics.
Yeah.
Is this a common strategy in numerical computation to shift values without changing their relative relationships?
Absolutely.
Okay.
It's all about working within the limitations of how computers represent numbers.
Right.
But this shifting doesn't fully solve the underflow problem.
Okay.
For that, we often need a separate numerically stable log softmax function,
Okay.
which uses logarithms of probabilities to avoid those extremely small numbers.
This makes me appreciate all the behind-the-scenes work that goes into making these algorithms work reliably.
Indeed.
Yeah.
And this brings us to another crucial concept,
Okay.
conditioning.
Conditioning.
It describes how sensitive a function's output is to tiny changes in its input.
Okay.
Think of it like a domino effect. A small nudge at the beginning can cause a cascade of increasingly large changes down the line.
We've seen how the softmax function needs careful handling to avoid errors.
Right.
But it's not just individual functions we need to worry about, right?
Right.
The overall stability of the system matters too.
Yeah,
That's where this idea of conditioning comes in.
exactly. Some functions are like those super sensitive scales that go out of whack if a fly lands on them,
Okay.
while others are more like a sturdy rock. This sensitivity is particularly important when we deal with matrix inversion, a fundamental operation in many machine learning algorithms.
Okay, so
Yeah.
matrices are these grids of numbers, right?
Yeah.
What does it mean for a matrix to be ill-conditioned, and why is that a problem?
An ill-conditioned matrix is like that super sensitive scale.
Okay.
Its output can change drastically with even the smallest changes to its input. Inverting such a matrix can amplify even the tiniest errors in your data,
Okay.
leading to unreliable results.
So even if we have stable functions like our tweaked softmax,
Right.
a shaky matrix can still throw everything off.
Yeah.
It's like building a house on unsteady ground.
That's a great way to put it.
Yeah.
On top of ensuring stability in individual calculations, we need to be mindful of the stability of the entire system.
This all makes it seem like doing accurate math on a computer is like walking a tightrope.
Yeah.
So how do we even begin to solve problems in this potentially chaotic numerical landscape?
That's where optimization comes in.
Optimization.
It's all about finding the best possible solution,
Okay.
either minimizing or maximizing the output of a function by adjusting its input values.
So we're trying to find the peak of a mountain or the lowest point in a valley.
Yeah.
But instead of a physical landscape, we're dealing with mathematical functions.
Exactly.
And what do you call the function we're trying to minimize?
There are a few terms you'll hear.
Okay.
Cost function, loss function,
Okay.
or error function.
Got it.
They all refer to the same idea, a measure of how bad our current solution is.
Right.
The higher the value of this function, the worse our solution is.
Got it. The higher the cost, the worse the solution.
Right.
But with so many optimization algorithms out there, how do we pick the right one for a given problem?
One of the most popular is gradient descent.
Gradient descent.
You can think of it like a ball rolling down a hill.
Okay.
The direction the ball rolls is determined by the negative gradient, which points towards the steepest descent. And the size of each roll is controlled by something called the step size or learning rate.
I can visualize the ball rolling downhill.
Right.
But how does that translate to actually finding the optimal solution in a complex machine learning model?
Imagine that hill as representing our cost function. Gradient descent takes small steps in the direction that most reduces the cost, effectively rolling down the hill until it finds a minimum point.
That makes sense, but you mentioned earlier that gradient descent can get stuck.
It can.
What did you mean by that?
Imagine that ball rolling down the hill.
Okay.
It might get stuck in a small dip or valley that isn't the absolute lowest point.
Okay.
In mathematical terms, we call these local minima.
Local minima.
And there's another potential pitfall.
Right.
Saddle points.
Saddle points, what are those?
Imagine a landscape that looks like a horse saddle.
Okay.
It slopes downward in one direction and upward in another. Gradient descent can get stuck in these spots too because the slope is 0 even though it's not a true minimum.
Ah, so it's like the ball getting stuck in a flat spot on the saddle.
Exactly.
Are there ways to avoid these pitfalls and make sure gradient descent finds the absolute best solution?
That's where more advanced optimization techniques come in.
Okay.
There's a whole family of them called second-order optimization methods.
Intriguing. So if gradient descent is like looking at the slope of the hill,
Right.
are second-order methods like looking at the curvature, the way the slope itself changes?
You're catching on quickly.
Okay.
They use more information about the function to take smarter steps and avoid getting trapped in local minima or saddle points.
Okay, so far we've been talking about optimizing a function without any restrictions.
Right.
But what happens when we need to find the best solution within certain limits?
Excellent question. That's where constrained optimization comes in.
Constrained optimization.
In many real-world problems, we have limitations on our input values.
Okay.
These constraints define the boundaries of our search space.
So it's like trying to find the lowest point in a valley.
Yeah.
But now there are fences or walls limiting where we can go.
A perfect analogy.
All right.
And one way to handle this is using what's called the Karush-Kuhn-Tucker, KKT approach,
Okay.
which involves Lagrange multipliers.
Lagrange multipliers. I've heard of them before, but they've always sounded a bit mysterious. Can you demystify them for us?
The basic idea is quite clever.
All right.
We convert the constrained problem into an unconstrained one by incorporating the constraints into the objective function itself.
So it's like adding a penalty to the cost function if we step outside the allowed boundaries.
That's one way to think about it.
Okay.
Lagrange multipliers help us balance the original objective with the need to satisfy those constraints.
So it's a balancing act between getting the best solution and staying within the rules of the game, so to speak.
Exactly. Now, to make all of this more concrete, let's look at a specific example.
Okay.
The linear least squares problem.
All right, let's see this in action. Tell me about the linear least squares problem.
In this problem, we're trying to find the best fitting line or hyperplane in higher dimensions to a set of data points.
Hold on, what's a hyperplane?
A hyperplane is just a generalization of a line to higher dimensions.
Okay.
Imagine a flat surface cutting through a 3D space.
All right.
That's a hyperplane. Anyway, finding the best fitting line or hyperplane is a classic problem with applications everywhere from statistics to machine learning.
Right, like fitting a trend line to stock prices.
Yeah.
Or finding the best linear model to predict house prices based on features like size and location.
Precisely. We can solve this using the optimization techniques we've been talking about.
Okay.
We start with a guess for the line's parameters, calculate the gradient of the error function,
Okay.
and then use that gradient to iteratively update our solution.
So we're basically nudging the line bit by bit, guided by the gradient, until we find the one that minimizes the overall error.
Exactly. And there are even more specialized methods,
Okay.
like using the Moore-Penrose pseudo-inverse,
All right.
which can directly calculate the solution in certain cases.
This is all making me realize that numerical computation is a delicate dance between approximation and precision.
That's a beautiful way to put it. And as we rely more and more on machine learning models to make important decisions, the stakes of this dance get higher and higher.
This has been incredibly illuminating. We've covered so much ground already.
We have.
What's next on our deep dive into numerical computation?
Let's explore how these concepts are being applied in cutting-edge areas like deep learning and scientific computing.
Okay.
It's a fascinating journey.
All right, let's do it. So we've been talking about finding the best fitting line or hyperplane to data.
Right.
But what if we have additional constraints? How do we find the best solution when there are certain limits or boundaries?
That's a great question.
Yeah.
And it takes us into the realm of constrained optimization.
Constrained optimization.
Imagine we're still trying to find the best fitting line for our data.
Okay.
But now there are restrictions on the line's parameters.
So it's like we're playing a game with specific rules.
Yeah,
We need to find the best solution, but we have to stay within the boundaries of those rules.
exactly.
What kind of constraints might we encounter in practice?
A common constraint is limiting the norm of the solution vector.
Okay, quick refresher.
Sure.
What does norm mean in this context?
The norm of a vector is essentially its length or magnitude.
Okay.
It's a way to measure the size of a vector, and sometimes for reasons like preventing overly complex solutions or ensuring stability,
Right.
we want to keep this size in check.
So it's like saying find the best fitting line, but it can't be too steep or too long.
Exactly. And remember our friend the Lagrangian?
The Lagrangian.
We can use it here too.
Okay.
We create a new objective function called the generalized Lagrangian.
Generalized Lagrangian.
It combines the original error function
Okay.
with a penalty term related to the constraint.
So we're back to the idea of penalizing the solution if it breaks the rules.
Right.
But how do we control the severity of that penalty?
That's where the Lagrange multiplier comes in.
Oh, yeah.
Think of it as a tuning knob.
You're right.
A large multiplier means the constraint is strictly enforced. A small one makes it more lenient.
Interesting. So it's like adjusting the height of those fences you mentioned earlier.
Yeah.
A high fence means we're very strict about the constraint,
Right.
while a low fence allows for more flexibility.
You've got it. The challenge is finding the right value for this multiplier.
Right.
We need to balance minimizing the error
Yeah.
with satisfying the constraint.
It sounds like a delicate balancing act. Are there any special tools to help us find this sweet spot?
Absolutely. One powerful technique is the Moore-Penrose pseudo-inverse.
The Moore-Penrose pseudo-inverse sounds like a secret weapon in the numerical computation arsenal.
It's pretty handy.
What makes it so special?
It allows us to calculate a generalized inverse of a matrix,
Okay.
which can be super useful for finding solutions even when a matrix isn't invertible in the traditional sense.
So it's like finding a workaround when the usual methods don't apply.
Exactly.
That's pretty neat. So how does this pseudo-inverse help us with constrained optimization?
It helps us find the solution that would minimize the error
Okay.
if there were no constraints. Then we check if that solution happens to satisfy the constraint.
So if the unconstrained solution happens to be within our fences, we're golden.
Exactly.
But what if it isn't?
Then we got to adjust.
Okay.
We tweak the Lagrange multiplier
Okay.
and solve a modified linear equation to find a solution closer to the feasible region.
So we're iteratively refining the solution until it meets both the accuracy and constraint requirements.
That's right. We keep repeating this process, tweaking the multiplier and solving the equation until we land on a solution that both minimizes the error and satisfies the constraint.
This constrained optimization stuff sounds pretty complex.
It can be?
Is it a common problem in machine learning?
Oh, absolutely. Constrained optimization is everywhere in machine learning.
Right.
It's how we make sure our models are not only accurate, but also well-behaved
Right.
and tailored to the specific problem we're trying to solve.
So all these techniques we've been discussing, stable functions, conditioning, gradient descent, Lagrange multipliers,
Yes.
they're all part of this grand puzzle of making numerical computation work effectively for machine learning.
That's right. These concepts might seem abstract,
Yeah.
but they're the foundation for training and optimizing those powerful machine learning models we hear so much about.
It's incredible to think that all this sophisticated math is happening behind the scenes whenever we use AI systems.
It is.
What are some other areas where these techniques are essential?
The applications are vast. One area is deep learning,
Deep learning.
where we're dealing with neural networks that have millions or even billions of parameters.
Right, those massive networks that can generate realistic images or translate languages.
Yeah.
Training those must be computationally intense.
Exactly. Training them requires careful attention to numerical stability and efficient optimization. Gradient descent, in its many variations, is a workhorse algorithm for training these deep learning models.
I'm starting to see how numerical computation is like the unsung hero behind the AI revolution.
It really is.
But it's clearly not just about AI.
Right.
You mentioned scientific computing earlier.
Yes.
How is numerical computation used in scientific fields?
Many scientific disciplines rely heavily on numerical simulations and models
Okay.
to study complex phenomena, whether it's weather forecasting,
Right.
climate modeling,
Mm-hmm.
drug discovery,
Yeah.
or even understanding the universe.
Right. Those simulations often involve crunching massive amounts of data and solving really complex equations.
Absolutely.
Yeah.
And that's where AI is starting to play a more significant role.
Interesting.
Techniques like deep learning are being used to speed up those simulations, improve their accuracy, and extract insights from data that were previously hidden.
So AI is not just changing how we interact with technology, it's
Right.
changing how we do science. That's amazing. But it also seems like there's a lot of responsibility involved.
Absolutely. The more we rely on AI for scientific discovery, the more critical it becomes to ensure the reliability and robustness of the underlying numerical methods.
Because a flawed simulation or a misinterpretation of the results could have serious consequences, especially in fields like medicine or climate science.
It could?
What's the key takeaway for someone who wants to go deeper into this world of numerical computation?
A solid understanding of calculus, linear algebra, and optimization algorithms is crucial.
Okay.
But beyond the technical skills, what's equally important is developing a mindset of awareness and critical thinking when it comes to numerical computations.
What do you mean by that?
It's about recognizing that numerical computations are always approximations.
Okay.
There are inherent limitations, potential pitfalls, and trade-offs to consider.
Right.
So always be questioning assumptions, checking results carefully, and considering different approaches.
So it's not just about plugging numbers into formulas. It's about understanding the nuances and potential for error in every computation.
Exactly.
It sounds like a fascinating field to explore.
It is. And as AI continues to advance, the importance of mastering these numerical techniques will only grow. What's fascinating here is that as we push the boundaries of AI, we are constantly encountering new challenges and pushing the limits of numerical computation.
So it's like a two-way street. AI is pushing the demands for more powerful and sophisticated numerical tools.
Right.
And those tools, in turn, enable even more advanced AI applications.
Exactly. And one area where this is particularly evident is in the realm of scientific computing.
Okay.
Shall we dive into some specific examples?
Let's do it. I'm ready to hear how AI and numerical computation are teaming up in scientific computing.
Okay.
What are some specific examples of this dynamic duo in action?
One really cool example is in the field of computational fluid dynamics.
Computational fluid dynamics.
It involves simulating the flow of fluids like air or water,
Okay.
which is crucial for things like designing airplanes, predicting weather patterns, and even understanding blood flow in the human body.
Those simulations must be incredibly complex. How is AI helping to make them more accurate or efficient?
Traditionally, these simulations relied on solving complex mathematical equations
Right.
that describe fluid behavior.
Mm-hmm.
But with AI, specifically deep learning,
Okay.
we can train models to learn those intricate patterns from vast amounts of data.
So instead of explicitly programming the equations,
Yeah.
we're letting the AI model learn the rules of fluid dynamics from the data itself.
Exactly.
That's pretty mind-blowing.
It is. And what's really exciting is that these AI-powered simulations can often be much faster than traditional methods.
Oh, wow. So that really speeds up the process.
It does.
So this allows scientists to explore a wider range of scenarios, design more efficient experiments, and potentially make groundbreaking discoveries.
It does.
That's incredible. It sounds like AI is giving scientists a whole new set of tools to tackle complex problems. Are there any other examples of this AI numerical computation partnership in science?
Absolutely. Another area is Drug discovery.
Drug discovery.
Developing new drugs is a long and expensive process.
Yeah, it is.
And a lot of it relies on simulating how molecules interact with each other.
So scientists are using computer simulations to predict how well a potential drug might work before they even start testing it in the lab.
Exactly. And AI is playing an increasingly important role in those simulations. By learning from huge databases of molecular structures and their properties, AI models can help identify promising drug candidates much faster and more efficiently.
This all points to a future where AI and numerical computation are deeply intertwined, not just in science, but in countless other fields.
I completely agree. And as these fields continue to advance, we can expect even more groundbreaking applications and a deeper integration between AI and the fundamental principles of numerical computation.
This deep dive has been incredibly eye-opening. We started with the challenges of representing continuous math on digital computers, and ended up exploring how AI and numerical computation are transforming scientific discovery. It's clear that understanding these concepts is more important than ever.
Couldn't have said it better myself. As we rely more and more on AI and complex simulations, a solid grasp of numerical computation becomes essential not just for engineers and scientists, but for anyone who wants to navigate this increasingly complex world.
Well, I've learned a ton today. Thanks for taking us on this fascinating journey into the world of numerical computation.
It would be my pleasure.
And to our listeners, if this deep dive has sparked your curiosity, keep exploring. The world of numerical computation is vast and constantly evolving, and there's always something new to learn.
There is.
So keep diving deep, keep asking questions, and keep pushing the boundaries of knowledge. Until next time.